Welcome to the next droplet. In this segment, we're going to be actually examining the techniques that are used in the Wolman Pebble count method. Wolman offered this technique back in 1954 as a means and a method of sampling coarse riverbed material, which has actually evolved into various applications and uses over the years. It's actually used to inventory the lining or the top layer of particles within gravel bed or coarser stream channels so that we can make various roughness estimates or various estimates of a stream channel. They can be used, as I mentioned, for estimating for instance, the Manning's roughness of a stream if we employ the Manning Strickler to the various representative grain sizes. It can also be used in sediment transport studies to give us an idea of what the grain size distribution is of the bed material. It can also be used in aquatic biology studies to actually understand better the distribution in grain sizes for different species that can be utilizing different habitat niches for spawning, rearing, and various other stages of life. It can also be used to evaluate bed stability by inventorying the particle sizes on the bed of the channel and then determining, based upon those sizes, some indications of do we have channel incision, for example, that's happening, or channel widening that's happening. So with all these different applications, there have also been advancements and evolutions in how this technique is employed. Here we're really going to use the technique to estimate the grain sizes for roughness. Now, the one thing that we have to keep in mind is for a roughness estimate is that we're trying to inventory the grain sizes within the entire wetted perimeter. That's where we're going to focus in on this inventory, within the entire wetted perimeter of the bank full or the main channel. There are some studies that actually just inventory the bed material sediment starting at the water's edge or simply on the bottom of the stream channel. Here we're going to go up the sides of the banks on both sides to the limit of the bank full stage. We can do both at the same time of both of those inventories. All we'd have to do is flag those particles that we're measuring from the bank full stage down to the bottom of the stream channel on both sides so that we could separate those or parse those out to just do the bed material analysis. A couple of other notes with respect to the technique is the fact of, well, we can either be evaluating something just at a particular morphological scale, such as a riffle and or a run, to quantify, for instance, those are the locations where we'd be evaluating stability analysis with respect to kind of better understanding vertical incision of the channel. But there's also reach basis analysis. So what we typically want to do then is identify what is the objective actually of the inventory itself. If it's just a stability analysis, well, we can go out and inventory or conduct pebble counts on 2 or 3 riffles along our steady reach, which is adequate and fine. If we're actually looking for a reach-based analysis, then we have to be looking at doing inventories on riffles and or runs, on bends, and any other morphological features that are along the length of the stream channel. Now, we don't need to do all of them along the entire reach of the channel. What we would simply do is identify before we even did a pebble count inventory or any other part of our field survey, the first thing that we typically want to do is we want to do a site walk to get a bit of appreciation for the general characteristics of the watercourse that we're inventorying. And then what we can do is simply enumerate the numbers of bends, the number of riffles, the number of runs, or whatever morphological features there, and then just develop an idea of how many features there are along the length of the watercourse. Identify what percentage of actually those features are on the watercourse themselves, and then choose a subset of those that represent roughly the same statistical patterns or features, and just sample a subset of those. So usually if we're doing a pebble count for a reach base, we're typically going to want to inventory 3 to 4 riffles and 3 to 4 bends along the watercourse. If we have a longer watercourse reach, of say 5 or 6 meander wavelengths, we can actually always just do a subset of that. We can, if we want to, do the entire reach of the study and each of the features, but this just gives us a way to actually still be representative of those morphological features. Some of the other things that we want to keep in mind is the fact that there's also techniques on each of the features of actually how to inventory things. Some users or operators prefer to go side to side, back and forth, similar to cross sections, or employing the velocity area method across the cross section. Others prefer to actually do a zigzag pattern from upstream to downstream along a morphological feature. Here what we're going to highlight is 4 cross sections or on a riffle that are perpendicular to each other, and that's so that we can also, sometimes we're also interested in seeing if there's any fining or reductions in grain size longitudinally from upstream to downstream as we traverse along the riffle. So we can even, although we're going to do a bulk analysis here, we could parse things out into each of the individual cross sections and actually see how, for instance, our D50 or our D84 is changing as we go from upstream to downstream on, for instance, a riffle. We typically expect actually a fining or a reduction in the grain sizes as we go from upstream to downstream. So it just, as long as we are inventorying the information consistently, we're able to typically parse a lot of that information out. The other thing is, well, how many particles should we collect per feature? Some studies suggest the fact that we should consistently be evaluating or counting 400 pebbles on every given morphological feature. Well, if we inventory 398 or 95 or 405, that's perfectly fine as well. But 400 seems to be a rather rigid kind of constraint, particularly when we start to look at scale. So the techniques that we use typically will identify as well, if we're in a stream channel that's usually less than 5 meters in width, that's the bankful width of the channel, we'll usually want to inventory over the length of that feature a total of 100 pebbles, roughly 100 pebbles. So that means on each cross section, roughly 25 pebbles that we're going to inventory. We scale that watercourse up between 5 and 10 meters, or 5 and 20 meters. Well, we typically will want to inventory then approximately 200 pebbles within the morphological feature such as a riffle and or a bend feature. So we would actually then have approximately 50 pebbles that are being collected on each given cross section. When we go above 20 meters in width, we usually relegate to the collecting 400 pebbles per morphological feature. So in other words, approximately 100 pebbles along each of the cross sections that we've inventoried. It seems like a lot, but actually it goes quite quickly in the field, and that's where we're going to turn to now.
So here we are in the field out on a point bar on a local gravel bed stream channel in southern Ontario, and we're going to talk about some of the nuances with respect to doing pebble counts. First thing that we have to identify is the axes that we're particularly interested in recording as far as the pebble count goes. So if you look around at any particular particle, and I'm going to choose an angular one to begin with, there are 3 principal axes. The long axis, which is what we refer to as the A axis, the B axis, which is the second largest axis, and the C axis, which is the smallest axis. And when we're conducting a pebble count, what we actually want to measure, whether it's with a caliper or a small little ruler, is we want to measure the B axis, and we want to measure whatever the width of that B axis is. In this case it is 41 millimeters in width, and as long as we're within, particularly on something of this size, of a millimeter or 2, it's completely fine and adequate. And the reason why we want to measure the B axis with respect to undertaking a pebble count is it's analogous to when we are actually putting material into a sieve, is that when we put material into the sieve, what is assumed that typically will fall through the sieve itself is going to be actually the particles that pass through the B axis. Typically if the particle is too large, it will not pass through, but usually things that are on the B axis will pass through the sieve. So we want to be consistent within that representation, because what a pebble count is similar to a sieve analysis, where the pebble count is simply measuring the number of pebbles that are counted and collected across a given morphological feature, such as a riffle or a pool or a run on a channel. We're going to actually determine our statistics based upon the number of pebbles that we actually count on each morphological feature. When we're doing things from a sieve analysis, where we nest the sieves together, we're going to mass the amount of material that's retained within each of the sieves. We have a total mass that passes through. Some might actually end up in the pan that we would then use in a hydrometer test, particularly if we're in a silt or a clay bed stream channel. And what we want to then calculate is the percentage of the particles that are retained between each of the sieves. So we want to do the same thing as a pebble count. Only difference is in a pebble count that we're actually just counting up the number of pebbles. Here we're actually massing the amount of material that's retained within each of the sieves. Brings us to an interesting other point with respect to the sieves, is the same thing that is done in the pebble count. This is something that people often do wrong in their analysis. So if we look at these, there's the sieves are nested such that the smaller sieves sit on top of the larger sieves. And so the assumption is that anything that's larger than this particular sieve size in here will be retained in this sieve. And anything that's larger than the next sequential sieve size will be retained in this sieve. So this sieve in here reads of 8 millimeters in size. This one reads as 12 millimeters in size. What is often done incorrectly is the fact that people will record the material retained within the smaller sieve size as that particular size. This is in fact incorrect. It's actually what you have to do is you have to calculate the median value between the two sieves that you've actually done the analysis on. Now sieves are actually recorded or calibrated in the millimeter size, but to the log of base 2. So you have to do things in terms of what's referred to as the phi scale. And you then calculate the median between two successive sieves based upon the phi scale, and then you convert that back to standard millimeter scales. It's very important with respect to the proper representation. The other thing that one can note is the fact of, well, if you're just doing a pebble count, what you typically want to just collect is the b-axis information. But there are some benefits to actually measuring all three principal axes of the a-axis, the b-axis, and the c-axis. If you're out on the stream or you're also particularly interested in collecting bed material samples or point bar samples, and those sample sizes can get relatively large, particularly if we're in a cobble bed stream channel, those cobbles can actually get to be quite significant in size where we cannot mass them even in the field. We can easily take a shovel and do a bed material sample in the field, and we can mass it in the field itself, but we'll get to a size where simply the scales that we can actually use out in the field become rate limiting with respect to how much they can support with respect to a load. But what we can extrapolate is the fact that if we've measured all three principal axes on all of our particle sizes, and then we can calculate for the ones that we can measure in mass on its scale, we can then actually see what the sphericity is, which is simply a ratio between the a-axis, b-axis, and the c-axis, and come up with a relationship for the mass and the particle sizes as a function of sphericity. We can then extrapolate that up to the larger particles to estimate what the mass is on larger particle sizes. The last thing that we can talk about is the fact of, well, we can either use a caliper such as this, or we could use a small ruler or a stainless steel ruler if we had that. We can also use a gravelometer. And a gravelometer is simply different calibrated sizes. Here it shows this is 128 millimeter size, 90 millimeter size, 60 millimeter, and all the way down to a 4 millimeter size in the smallest hole. So we can do a pebble count by passing the particles successively through each of these sizes, and this automatically puts them into the various class sizes. Now the challenges with this, that this can be a relatively slow process compared to actually doing a pebble count and recording the values. So the choice is yours with respect to which option that you want to actually undertake a pebble count of. Now when we get to the small grain size fractions, that becomes also something of a bit of a challenge, because it's very difficult to measure things below 2 millimeters. So something as calibrated as this grain size chart, which actually shows different grain sizes, and they've been calibrated to the sieve sizes, identifies the different grain sizes. So we can actually collect some grain sizes actually in the field, compare them to the little chart here, and estimate what the particle sizes are. The other way that we can do that is we can actually have a small jar of the various particle sizes, and we can actually test those with our fingers from time to time, and we can actually calibrate our fingers to the different particle sizes. So we can use that as a field calibration method as well. Thanks for coming out to the field with us.
So here we are out in the field. As mentioned in the first part of the video, is that we're going to begin our inventory at the bankful stage. So here what you notice is that the first few are actually very fine sands, and they're being enumerated within the spreadsheet, or coarse sands. And as soon as we encounter any particles, the technique that's actually being employed here is that you don't look into the stream channel at the particle you want to pick up. If you'll notice, I'm looking away, my head is turning away from where I'm pointing. I'm pointing into the stream channel with my index finger, and the first thing that my index finger touches, I will pick that up and then measure the b-axis of that given particle. If I detect it's a sand or a fine grain material, I'm going to rub that sand or that silt or that clay between my index finger and my thumb, to detect, based upon a textural analysis, what I believe that grain size to be, and the recorder is then going to record what that information is. And I'm simply going to go along. As you notice, I keep turning my head away from where I'm grabbing the sample, and I'm going about 1 footstep away from where I'm inventorying. The other thing to note is, as I'm going, taking a sample, I'm not putting it back exactly where I actually removed it from the bottom of the stream channel. I'm actually throwing it between my legs and a little farther downstream, so I'm not resampling those particle sizes as I go along. And then this just becomes an iterative sequence of picking up, pointing down to the bottom of the stream channel while turning your head away from the location where you want to sample. And there's a bias that is indicated where, if you are looking at what you're sampling, a tendency that many people have is to actually always be picking up a larger particle size. So we want to always turn our head away as we're inventorying things to conduct that inventory. So here, as we near the edge of the stream channel, again, what we're going to make note of is that we could have just done the bed inventory of the stream channel, which is consistent within some inventories, but here we're going to actually go all the way up the wetted perimeter up to the height of the bank flow channel. And now what we're actually going to do is we're going to switch users. And we have the other user, a person out in the field, that's now going to sample, and the other person is now recording. This is one technique whereby that you can actually minimize bias within the sampling, at least remove some of the systematic biases is there. Now you've also then introduced the potential for another random source of error between the two samplers. We found over time that it's a way to switch off and to minimize some of that user bias within the inventory. Now what we are doing is, if you notice that we haven't actually strung a tape measure across the stream channel or anything else to identify exactly where we are sampling, we're going to be based upon that on experience. We can typically wade across the stream channel once, assess whether are we in a 5 meter wide stream, a 10 meter wide stream, a 20 or a 50 meter wide stream, and then we know based upon that of, well, if we're in a 5 meter wide stream, we're going to collect typically about 25 pebbles across the cross section, and then so we just kind of visually gauge what that distance is in our sampling inventory based upon that. And here again, we've switched users again. The other person is now doing the substrate inventory while the person is recording, and we're recording this actually on a sheet of paper that actually has little tick marks for that we can actually tick off to indicate the medium sands or medium sands. The recorder is not actually writing medium sand each time, that they're just ticking it off of what it is. Within a box that identifies a medium sand and a grain size. For the purposes of this example, we in fact actually did write down medium sand or MS or FS for fine sand or coarse sand, for example, for the sake of this illustration. But if we're doing it in the field, we're just going to use ticks to tick off. If somebody identifies it as a fine sand, we identify that box where the fine sand is noted. We tick that box to identify that we've counted that once. And maybe we end up with 10 or 20 or 50 or 100 ticks, or 34 ticks, for example, of that particular grain size. And then we're finally getting down to the last, or the most downstream cross section within this morphological feature in here. And so what we've also done is we've identified, based upon our initial field reconnaissance in here, what the distance was of that morphological feature, in this case a riffle, and then we've just simply visually broken it up into 4 approximate equidistant cross sections starting from the upstream to the downstream end. We also know that typically on riffle features that there's a fining from the coarsest material on the upstream limit of the riffles, and it actually progressively decreases in average size of the D50 and the coarser grain sizes as we go from upstream to downstream. This particular method of actually inventorying the cross sections rather than a zigzag pattern across the stream channel itself provides us with the opportunity and the ability to go back and then, if we want to, look at each one of the cross-sectional inventories that we've actually done from this pebble count to then identify what the differences are in the grain size classes from upstream to downstream. And then we do a similar process if we actually got to a bend as well. The only limit in the bend is we can only go into the bend as far as we can actually wade safely. Thanks for coming to the field. Now that we've returned from the field from doing our pebble count, back to the office, back to our field camp, or back to our residence, it's time to actually process that data. So what we actually have here in the spreadsheet is the data that we actually inventoried out in the field here in column A. And you'll notice in here that we have short forms for various particle sizes, and these relate to particle sizes within the sand range that we were identifying out in the field. What we would typically do in the field is, rather than actually having them written out for every line or every inventory that we would be doing out in the field, we would simply have, as was mentioned before, a little sheet where each row would identify the various sand particle sizes: very fine sand, medium sand, coarse sand, and very coarse sand. And every time that the sampler would actually identify one of those particles, we would simply put a tick beside that so we could enumerate them that way, which is a lot more efficient. Here we actually identified each one of them in the field inventory this time for the purposes of this example for completeness. So one of the things that we want to identify is then, well, converting these short forms into given particle sizes so we can do a data analysis upon the whole inventory. So if you'll notice here that we have, for these particle sizes, we have size descriptions, and everything falls into what we refer to as the Wentworth grain size classification, which is a relatively universal classification that's accepted for doing grain size analysis, in particular when we're doing geotechnical studies or any type of grain size analyses. It's based upon the phi scale, and the phi scale, if you recall, is a phi unit is equal to 1 minus 1 times the log of the particle size divided by the log of 2, or in other words, minus log to the base 2 of what the particle sizes are. Here what we actually want to then do is, because everything else has been inventoried that we collected out in the field in millimeters, we want to convert these values to millimeters as well of what we encoded for the sand sizes. The other thing to notice in here, just as we're looking at the Wentworth grain size classification, is that the smallest particle sizes, or clay, are associated with the largest phi unit values, and the largest particle sizes are associated with the smallest, or the most negative values in this case. So it's a bit counterintuitive with respect to particle size and the phi unit scale, but from an analysis perspective and representing grain sizes because of the broad spectrum and ranges over several log scales, that the Wentworth grain size classification and the phi unit scale work quite well in those cases. The other thing that's important in here is to recall the fact of what we're representing as a representative grain size between each of those classes. This would be analogous to having sieves, where we would have a coarser sieve sitting on top of or nested above a finer sieve, and we'd have sequentially finer sieves as we went down our sieve series until we actually had the fine-grained silts and clays falling through into a pan on the bottom. So the threshold between any two consecutive sieves then, the particles above that are whatever falls through. The particles on the next sieve down are only what's retained between those two sieve size classes. So that the representative particle size of that size class is not the particle size that just didn't make it through to the next size class. It's actually the median value, or the average value between those two size classes, and that's based upon the phi scale. So we want to actually represent our grain sizes when we convert them back to millimeters as the average based upon that phi unit scale. So let's first actually do our conversions from our phi unit scale back to our millimeter scale. So we want to then identify then that, well, if we're calculating the average median value, well, this is the next larger particle size up in here, which is the 2 on the phi scale, to 3, which is the next smaller particle sizes. So our average value of that is equal to a value of 2.5, which is then that being reflective of a fine sand. So let's convert our phi unit scales back to millimeters first, and that's going to be equal to 10 raised to the power of minus 1 times our phi unit of our median range times the log of 2. And we're going to assign that to all the various size classes. And then we're going to do the same thing to the threshold sizes. So now we have particle sizes in millimeters that are consistent with what the rest of our inventory was in. And this is more intuitive, where you have the the clay, which is the smallest grain size, associated with the smallest particle size in millimeters, and the boulders being associated with the largest particle sizes. So let's then now assign for these various values in here our representative particle sizes, and remember that we're going to assign the median values to those and not the size class threshold. So for convenience in here, I'm just going to sort all of the data that we collected from our pebble count in the field. I'm just going to constrain it to one column in here. And I'm first going to sort from largest to smallest so that all of my encoded ones are up at the top. And although we have a spreadsheet that does this automatically, what we wanted to do is actually to go through the steps to show that you all have to do this. So we're going to assign that, and I'm just going to paste the values, because if I paste the formulas, then they're not going to transfer properly. My values for the median sands and for the fine sands. And then for the coarse sands. And because this was sorted based upon the numbers in the alphanumeric sequence, it doesn't necessarily mean that these are going to be sorted in the right order now. So I'm just going to go ahead and resort this now from the smallest to the largest particle size. Alright, so now our particles are sorted from the smallest to the largest. I'm then going to actually calculate the percentage of the particles that are passing a particular grain size or a class threshold at any one time. So I'm just going to enumerate the particles first, count up the number, and then so I have 217 particles, and then I'm going to calculate the percentage. It's divided by, and I'm going to count the number of particles. Times that by 100. So that gives me my first value, and I want to do the same thing all the way down, but I want to keep my first row and my last row the same, so I'm just going to constrain that to the same conditions. And then I'm going to calculate my percentage. And at the end down here, I should be ending up with a value that's equal to 100%. In fact, that's what I have. And I'm just going to convert now my millimeters to phi scales, because I'm going to do all of my grain statistics based upon my median phi unit scale in here. So this is equal to a value of -1 times the log of my particle size divided by the log of 2. And my smallest particle size should then be associated with the largest phi unit value. And down here at the bottom, when I paste this, it should end up being the smallest value, which is -6.3. So now I have everything converted to phi scale. I have it sorted from the smallest to the largest particle sizes. I can now then start to do my analysis. So the first thing I want to do is I want to bin all of the data that I've collected out in the field that's now converted to phi units, and I want to bin it into the various median size classes in here. So what I'm going to do is I'm going to identify, I want to look at the frequency, or simply count up the number of particles in each of those size classes. So I'm going to identify the range that I want to do the size classes in, which is going to be coincident with the number of rows I have for my median phi values. And then what I want to do in here is I'm just going to re-highlight those rows, and then I'm going to type in here frequency. And then I'm going to choose what the data I want to do the analysis on, which is this row here. And then I want to then bin it by my median size classes. So those rows there. And what's important in here is I have to close the bracket. Now if I were to just hit return, it would only assign a value to row number 3 in here. So to actually get the frequency done properly over the entire range from the smallest to the largest particle size, what I have to remember to do is to hit and hold Control Shift and then hit the return key. And that now gives me the number of particles within each of the grain size classes. So now they've been counted and sorted. So all I have left to do is determine the frequency. I have down here at the bottom is the total number of particles within my analysis. This coincides with my count. If I go back in here, down to the bottom, so I am counting the same number of particles. So I'm basing my analysis off the same values. And then my frequency percent is just the percentage of each of those particle classes within my entire analysis. So all I have to do is take that, divide it by my value at the bottom in here, multiply it by 100. And I'm going to constrain, because I want everything to be compared to my total number of values in here. I'm just going to constrain that value in here. And then my cumulative percent, well, the first one is the associated value in the frequency analysis. My cumulative percent is the one above plus the one in the same grain size class. And then I just paste that all the way through. Now the next thing I can actually do then is evaluate my various percentiles that I'm interested in, the D16s, the D25s, etc. So I can do this graphically off the graph, which is the same thing of actually doing it off of my percent finder within this inventory. So the first thing I'm going to look at here is my D16 value. So I'm just going to scroll down the list until I intercept a percentage that's just slightly greater, just the first one that's within the value of 16% or larger. I'm going to copy that grain size. I'm going to paste the value. I'm going to look down here, and just for convenience I'm going to split the line in here just so that we hold everything constant above that. Looking for my D25 threshold, which is that value. Looking for now my D35. Particle size that's associated with that. My D50. D65. And I'd use this information in my analysis. And finally the D84. And I can also then do this off of my bin data for my statistical analysis as well. So I'm looking for D16, where is the D16 occurrence? It first occurs in here. So that gives me my median grain size. Remember, I'm not choosing my thresholds, I'm choosing my median grain sizes. And then I'm going to look for my D25. D25 meets that threshold there. My D35 is within this grain size class. D50. So my D50s are essentially the same value. My D65, same grain size class. So this is where the binned information can sometimes be a little bit misleading, or it's actually showing a skew in the distribution of the data. 75, because they're all being represented by the same grain size class. And the D84. So now I have the information evaluated in two different ways. Now I can take that information, and I can now graph that, and I can look at grain size distribution, and again I'd be looking at the median grain size as my representative grain sizes, and I can plot my frequency distribution if I would like. So I typically will plot this as a bar graph that's actually showing the percentage of each particle size class within my grain size pebble count analysis, or I can actually plot this again as my median grain size and then as a function of my cumulative percent of my distribution. And then I can do my analysis and then look for any biases within the data itself. Glad you came out with us on this field campaign.